But what I do want to do is quickly brush through and review a lot of the stuff we talked about yesterday. Okay, we talked about specific heat, correct?
Yep. Yeah.
Basically what specific heat was kind of told us how fast something will heat up or how slow something will heat up, correct? Okay, if something heats up relatively quickly, what could be said about its specific heat?
Low.
Low. Okay, what is that going to look like on a heating curve when it comes to, okay, steep slope? Okay, and I showed you that yesterday, right?
Yes.
Okay, and if something takes a long time to raise the temperature or heats up relatively slowly, what has to be true about its specific heat? It has to be high, and what you see is a more gradual slope, okay, instead of a steep slope, because you get a temperature change that's slower. Okay? And I gave you a few examples. Right here. Most of your metals, as you would have probably anticipated, are the ones that have low specific heats, because we know metals tend to what? Heat up quickly. Maybe it was too broad of a question. Okay. The whole purpose of specific heat, right? And then we had our random water that was kind of an outlier, and it kind of is an outlier in a lot of different things. We talked about it being an outlier in the fact that solid form is actually less dense than the liquid form, which is not usually the case in most things. Yep.
Okay, so I understand that like metals would have a really low specific heat, but why is oxygen still like a gas still less than a liquid in its specific heat?
Less than a liquid. Oxygen.
This
is regardless of the state.
I mean, like, okay, so like.
Why if it's bonded to
solids,
hydrogen?
liquids,
Well,
and gases, why isn't it in like order, like for specific heat?
not sure what you're asking. In
Like,
order.
wouldn't solids be the least and then gases be the highest?
For how fast they heat up?
And then
I think it's the
gases.
same for all of them. The temperature, like the amount of energy required to get a gas molecule of oxygen to raise 1 degree is going to be the same as it takes a solid molecule to raise 1 degree. It's just the gas molecule has higher energy to begin with. Doesn't that make sense? Is there a question about that in the homework? Now, I don't know this for sure. There might be a slight difference in specific heat based on phase, but not that I'm aware of, at least off the top of my head. So regardless of what phase it's in, it will take the same amount of energy to raise the temperature. It's just when you're in gas form, you're already at a higher temperature. Okay. Then we did this equation, which I said was kind of the calorimeter equation, and we figured out how much joules of energy was absorbed by the water, and we said we can use that idea to figure out how much energy was either absorbed or given off by the chemical reaction, right? Right? And the usefulness of using a calorimeter to study the enthalpy of a reaction, which we said enthalpy was essentially what? Heat transfer? Yep. Okay, we did these two problems. What does changing mean? Delta.
Difference. Oh, final minus initial.
Final minus initial. Yep. Okay. Then I showed you this equation, but we didn't really use it. And this is the equation that was how you would do 6 and 22. Okay. Now, what? I'm gonna write this up here. It's always the product's enthalpy minus the reactant's enthalpy. And the numbers that we used to put in here were the enthalpy of formation numbers that I think we ended on yesterday. Okay, we talked about this already. I showed you these graphs. Do you guys have any struggles with these graphs? Anything you want me to re-clarify on some of these graphs? Are you guys able to understand that negative exothermic release of energy? That's why we have higher energy reactants and lower energy products, more stable. Okay, and I think I showed you the chart, and did I not show you the chart and show you that most of the formation values are what? Negative. And the reason why most of the formation values are negative is because when they bond, they usually bond to become more stable. That's the purpose, right? Okay? That's why most of those values in the table were negative. Now, are there some things that require energy to form? Yes. There are. We talked about where the heat is located in a chemical equation. If it's a product, what would we say it is? Exo or endo? Exo. Release, product. If it's a reactant, it's required, and we would say it's what? Endo. Okay. Alright, then we began talking about this, which we said the formation values. How much energy would be either given off or absorbed when you form a particular chemical compound? Now they did start with a standard, right? And they said there are some things that are zeros. What was the important information for that? Okay, and that would also include like a diatomic guy, which one kind of element. For example, hydrogen gas most naturally is exhibited as H2, so they use that as it's naturally in that state, so it's got an enthalpy of formation of 0. Okay, and I think we looked at the table and we looked at a few of those that were zeros. Just so you know, if you're doing a problem, you can quickly know that they're 0 without looking into the table to find that they're 0. Does that make sense? That's just a quicker way of, that way you don't have to look when it's just an element. So for example, if I were doing, I would really just need to find the enthalpy of formation of that because I know these are 0. I don't have to look in the table because they're lone elements. So it's just a time saver more than anything. Okay. That's where that came in. Okay, let's do this one. Everyone turn to can someone find that page that has the table on it?
345.
Tell everybody what page that is on.
345.
Okay, 345. Get there, please, for me.
Can we use this on the test?
I will give you the enthalpy values for what you need. I'm not going to give you like the whole table. I'll just say the enthalpy of formation of this number, of this compound is this. You said 3 what?
45.
44.
So this first one's going to be easy. First off, we said we're going to use the enthalpy of formation numbers which come from this table, and we're going to use those numbers to plug into this particular equation. This is your overall reaction energy change. Okay? If you can figure out the amount of energy of your products and the amount of energy of your reactants and take the difference, you're going to find the change for your complete reaction. So, first and foremost, what can we quickly conclude about these two guys? They're 0. So, if I'm doing my change in H of my reaction, products minus reactant, so I'm going to start with the products. I need to find the enthalpy formation number of that. So, look in your chart, find NO2. Now, the phase is important. Now, there's only one NO2 number on here, but if you look at water, there's a different number for gaseous water and a different number for liquid water, and so forth. So, do I have a second
Yeah.
amen on that?
Amen.
33.2. What is the unit?
It's KJ per mole.
KJ per 1 mole. Now here's the little swerve that we have to take into consideration. Okay, that's how much kilojoules. Now, is it positive? It was a positive number?
Yeah.
Okay, so actually, this is going to require energy because it's positive. Okay, per 1 mole. How many moles do we have though?
2.
We have 2.
That's what I was saying last night.
Does everybody understand that all of these values in the table are the enthalpy of formation per 1 mole. Well, in balanced chemical equations, we could have more than 1 mole in the ratio or the recipe. Does that make sense? So what I'm going to have to do is I'm going to have to take and multiply by 2 to cancel out moles. Okay, so this would be your products. And technically, we would subtract our reactants, but we know they're what? But I do want to make sure that you understand that this would be 1 mole. Technically, it would be 1 mole times 0, right? Plus 2 moles, also times 0, which still gives you 0, but I'm just kind of showing you the process that you're going to have to run through your head when you're doing this. You need to find the formation value in the back of the book, and then you need to multiply them by their coefficients, because those numbers in the table are per 1 mole. Okay? So when you do this, the answer would be what?
Negative 66.4.
Negative?
Why would it be negative?
Oh, wait. Positive.
So your answer would be this, and here's how you should make sense of what this number means. Okay? When you perform this reaction here, okay, where these guys react to produce this, it requires this much energy to react. Why do I say requires?
Because you could have more.
Because it's what? It's endo. How do you know that that is an endothermic number? It's positive. Okay? So this reaction isn't a favorable one, actually. In fact, you have to put more energy in even to get it to react. So you can make the distinction that technically these guys are more stable than that is. Does that make sense? Okay, let's do a little bit more difficult one. Do you have any other in your notes? You might have to just write this in there. Alright. Okay, last thing before I get to one more difficult problem is this here. What does this say?
Standard state.
Does that sound like anything we did like a couple chapters ago? STP. Okay, but it's not the same. What's STP?
It's
273 Kelvin.
at 1 degree Celsius.
Which was really 1 ATM and equivalent to 0 degrees Celsius. Correct? Now, there's a really logical reason why they changed when they were doing these enthalpy values that they got from how they came up with this chart here. Why they used it standard state and not STP. Anybody have any idea why they would have used standard state to get these values versus STP like they did in the gas chapters?
Because otherwise it's gonna be weird.
Otherwise it'd be weird.
The numbers look not as understandable.
Okay. What are you gonna say?
Because it's dealing with energy, not pressure.
Yes, you're on the right track. Why would we want to do heat things at the freezing temperature? We'd probably want to do heat things around room temperature, right? That'd probably make a little bit more sense than doing heat standards at 0 degrees Celsius.
Yeah,
Does that make sense? Okay, so what they did is they chose the standard temperature for doing heat problems to be 25 degrees Celsius, which is about room temperature, depending upon what you consider to be room temperature. Why does it matter? Convenience. Yeah, you would ultimately, you're going to get the same proportions. It's just for an ease of not having to do it 0 degrees Celsius weather, not weather conditions. Yeah.
Like physically?
Yeah. Yeah, it's easier for, yeah. And also, you're gonna have different heat loss. So it makes the most sense. Now, I do want to. Okay, this isn't overly important, but I probably should mention a little bit about it. Okay, so standard molar enthalpy of combustion, this is just going to be your energy change that are involved in combustible reactions. Do you guys know what combustion is? Fluid.
We don't have this in our notes, should we write?
You don't? Probably not that important. That's probably why I was just going to ignore it. Yeah, ignore it.
Okay.
Basically what it is just a very specific version of what we've talked about. This would be just specifically for combustible reactions or any reaction involving oxygen, where you're doing a reaction in the presence of oxygen. So like burning gasoline, things like that. Let's end on this then. I'll give you this. You're going to have to find a spot to write this in, 'cause I don't think this is in your notes. To find the overall energy either given off or absorbed when this reaction occurs. It will always be one of the two. Either these will be more stable than these or less stable. If these were more stable than these, what would the sign of your H value be? Negative. If these are less stable than these, they're going to be positive. Because stability means low energy, right? Or lower energy. So what we're going to do here is we're going to use this equation along with the table in your book. Okay? To be able to figure out the energy change for this particular reaction. So, remember, very important. A lot of times kids will know when this is products minus reactants, but they're just so used to starting and going left to right that they just do the reactants first. So be careful. You want to do the products first. Okay? So.
It's unbalanced.
Is it?
I think it should be probably 3 on the first one.
Okay, hydrogens are balanced. Nitrogens are balanced.
No, it's balanced. Oh no.
Oh,
No,
no.
2, 4, 6.
Huh, they're not.
No, because on the
It should
second
be
here,
03
there's another. Yeah.
on the first one.
Yeah, that was 7 O's on the side.
This is 03?
No, the other one is 02. Instead of 02.
Oh.
On the left side.
Yeah, I see what you're saying. I must have wrote it wrong.
No, not left side.
The first one's H.
This is 2?
Yeah.
That's
That should be 3.
Okay. Let me just quickly look, check. Oh, yeah, you're right. I have it right here. I just wrote it wrong. Okay. Yeah, good catch. Now is it balanced? Okay.
I don't know why you looked at me.
I don't know why what?
That's
Why
funny,
you looked
it's
at her
actually
like, is it
yeah.
balanced?
I don't know. Yeah.
No, you just had like a kind of like a confused stare on your face, so that's why. Oh,
Just-
I'm really confused. Sorry, I apologize. I just wrote it wrong. So here's what we're gonna do. We're gonna start by doing the products first. And RXN, if you haven't figured that out, is abbreviating what? Reaction. Okay. It doesn't matter which one you start with. I usually just go left to right. But remember, we have to account for what?
The amount of moles.
How many moles we have? So I have 3 moles of my NO2. Make sure that you have the states right, because like I said, sometimes in your book, there is different states of the same thing, and they do not have the same enthalpy of formation values. Okay? what is the number that they give us in the book for NO2 in the gaseous state? Everybody understand where we're getting these numbers and how we get them? 33.2 kilojoules for every 1 mole. Everybody good on that? Okay. I'm going to add the other product. How many H2Os do I have? Be careful. Liquid water.
Negative 285.8.
Everybody figure out that there's actually a gaseous water in there as well?
Yeah.
Okay, they have different numbers. Okay? I'm going to close these brackets. It's the sum of your products minus the sum of your reactants. Okay? The reason why I'm going to put brackets here is because if you aren't careful, sometimes you just distribute the negative to the first one, but don't distribute it to the second guy. Do you understand what I said? You're subtracting both the reactants. If you're not careful, if you set it up in your calculator, try to do it all at once and don't get your parentheses worked out, it will just subtract the first one and will not do it to the second one. So, 2 moles. What was the number in your book for HNO3?
Negative 174.
Okay? And NO in the gaseous form, we only have one of it. Okay, solve. Honestly, solving this is probably the most difficult part about this type of stuff. Making sure that you distribute the negative correctly and you keep track of the negatives that are in there already. So try to figure this out. It's one of those lessons that's just a wee bit too long. I'm gonna make some modifications. If you have to break it up into smaller pieces, do it. That's fine. What? Okay, what'd you get? What'd you say?
I was just saying, and that's joules per liter.
Kilojoules, yeah.
Kilo.
You might not get this. Yeah, the most difficult thing is keeping track of the negatives when you do these. Did you get the 70.7? Brevin, did you get the 70.7? Maddie? Okay. You guys get 70.7? Rachel? Tanner? So we're good? Shelby, Tyler, Colby? Natalie? 70.7? Okay, here's what I want you to do for the remainder of the day. Work on 6 and 22. Okay? Cool?
Cool.
Thanks, Brian. For a while. negative 180.2 is the answer to the first part? Is that what you're saying?
Like 0 minus.
No.